Hi. In this final lecture on group theory, in the last lecture we will cover some leftover topics, including subgroups of cyclic groups and also cosets of a group. Okay, so basically let us come to back to cyclic groups again. I hope you remember what is a cyclic group. A cyclic group is a group G which is being generated by an element A. Okay, that means G can be written as like this, that is every element of G will be a power of an element A. Oh, so if there is an A like that, we will say that the group is cyclic and it is being generated by A. Okay, so we have seen examples of many cyclic groups earlier. Today we will be discussing about the subgroups of a cyclic group. So let us look at the subgroups of a cyclic group. Okay, subgroups of a cyclic group. Okay, so I also hope you understand what do you mean by subgroups. Okay, so we'll prove here that subgroups of a cyclic group are also cyclic. So that's the important result in this section. We'll also prove this. It's very simple. So it's basic number theory here. So let us take the setting now. Let us take a group G which is being generated by an element A. Okay, suppose G is being generated by an element A, and let us take a subgroup H. Okay, this A need not be in H. Okay, so it is not necessary that A is there in H. So anyway, H will have at least one element called identity. Okay, so because H is a subgroup, it should contain the identity element. So if there is only identity element, definitely it is cyclic because it is being generated by E. Okay, so H also will contain some other elements, where there can be B, C, etc. But all these elements are actually powers of A. Okay, so remember, A need not be there in H. There will be other elements in H, but those elements will actually be powers of A because G is cyclic. Every element of G can be written as powers of A. Okay, so it will contain some other elements, and now we'll show that this H is cyclic. Okay, so how do you show that? So let us let B be the element in H which has the smallest power of A. So let B be an element of H with the property that B is equal to maybe some A raised to R, where R is the smallest positive integer with that property. Okay, so we can always take it like that because why? Because you know that H is a subgroup and G is a cyclic subgroup. Therefore, every element of G will be power of A. Every element of G will be power of A. So all the elements of H also will be a power of A. Okay, so out of this you take the smallest power. Okay, so suppose there is A raised to 2 is there, A raised to 3 is there, I will be taking this A square. So I am taking B with the property that it is the uh, smallest element with the element with the property that it can be written as A raised to R, where R is the smallest positive integer from that set. Okay, so that means suppose it contains elements like this, so it will contain E. Of course, E can be written as A raised to 0, but it is not a positive integer, and there can be other elements like A square will be there, A cube can be there. We don't know what are there, so A square is there, A cube, there can be other elements also. So after this, this is the smallest positive integer with that property, so I'll choose this A square as my B. So that is how we are going to choose this B. Okay, so B is the smallest positive integer. So that's the key here. B is the smallest positive integer with that property. Okay, so we'll now show that this H is actually being generated by B. We'll show that this H is actually being generated by this B. So how will you show that? So if you take some other elements, maybe if I take some C, I have to show that C is a power of B. Okay, so if I take some C, I will show that C is a power of this B. So how will you show that this? So very simple. So actually B is actually A raised to R, right? Okay, so B is actually A raised to R. Okay, so I will take the element C. Okay, this C can be written as some A raised to maybe some A raised to N. Why? Because C can be written as A raised to N because our group G is cyclic. So every element is a power of G. So C can be written as A raised to N. Now I will divide this N with this R. I'll divide this N with this R. So what will I get? I'll get a quotient and also I'll get a remainder. So maybe I'll call the remainder as some T. Suppose T is the remainder. So this N can be written as Q into R plus T, and since T is the remainder, it has the property that 0 is less than or equal to T, which is strictly less than R. Okay, so since T is the remainder, it will always be less than R. So this has the property here. So that means my A raised to N, which is actually my C, can be written as A raised to QR plus T by the division algorithm because N is can be written as QR plus T. So this is actually equal to A raised to Q R into A raised to T. Okay, so that means my A raised to N is now actually A raised to qr sorry, a raised to qr into a raised to t. Okay, so from this result I'm going to just write down the value of a raised to t. So my a raised to t will actually be what? How can I write this? This will actually be a raised to n into a raised to minus qr. I will be dividing this to, I will be taking this a raised to qr to the left side. So this will be actually be a raised to n into a raised to minus qr, which is nothing but c into I can write it like this: a raised to r minus r the whole raised to q. C into a raised to minus r all raised to q. Also simply I can write this as c into a raised to r the whole raised to minus q. When you multiply, you'll get the same answer. Okay, so look at this. Okay, now you know that my H is actually a subgroup, so it will be closed. Now my C is there in H, my B is there in H, my B is a raised to r, so their combinations should also be there in H. Now you look at this. Now C is there in H, a raised to r is actually b, it is there in H. Now if you take any powers of a raised to r, it should also be lying in H, because H is a subgroup, it is closed under the operations. So if you take b square, b raised to minus 2, b cube, etc., everything should be there in H. So C is there, this is there, so their combinations also will be there. That means this element will be there in H. This is because H is a subgroup and it is therefore closed under the operation. So that means you get that actually a raised to t is there in H. But what do you mean by this? This t has the property that it is 0 less than or equal to t, which is strictly less than r. Now is this possible? No. Why? Because r is the smallest positive integer with the property that a raised to r is element of H. Now we have obtained another element t with the property that a raised to t is element of H, because and also t is strictly less than r. So this case is possible only if this t is actually 0. So this is possible only if t is actually 0, because r is the smallest positive integer with this property. So we will get that our t is equal to 0. That means what is actually this t? This t was actually the remainder when n was divided by t. So it is actually n is equal to qr plus 0. That means n is a multiple of r. What is actually this n? N is actually our c, right? So we took first an element c. We chose to show that this can be written as a power of b. So first you took c as equal to a raised to n. First you took this c as a raised to n. Okay, now we have obtained that n is equal to some q into r. Okay, so that means this can be written as a raised to q into r, that is actually a raised to r, that is actually a raised to r the whole raised to q, that is actually b raised to q. So that is, what do you mean by this? This means that if you take any other element of H, it can be written as a power of this, this can be written as a power of this b. So that means every element of H can be written as a power of b, that is actually, that means this is a cyclic subgroup. Okay, so what does that mean? The subgroup of every cyclic subgroup is also a cyclic subgroup. Okay, so let us turn to the proof once again. So we had a group G, that means every element could be written as a power of this a, some a raised to n. Okay, now we took a subgroup H. Okay, so the subgroup of H may not contain a. If it contains a, of course our answer is done. Okay, it is done. So it anyway will contain identity will be there. So it contains some other elements. So out of that we chose the element B with the property that it is the element with the property that it can be written as a raised to r, where r is the smallest positive integer with that property in that set. Okay, so r is the smallest positive integer of all those elements. Okay, so maybe H will contain, E will be there, A square will be there, A cube will be there, A raised to 5 will be there. So out of this, A square is the smallest, so this 2 is the smallest positive integer. So we are choosing B with that property. So B is the A raised to R with the smallest positive integer, where R is the smallest positive integer with that property. Okay, now we will show that this H is cyclic. So I will generally take an element C in H. I will show that this C can be written as a power of this B. Okay, so I will show that C can be written as a power of this B. So I will do that. So anyway, C can be written as a power of A, because A is group is cyclic, so it can be written as a power of A. Now I will divide this N with this R. So that means I will get the remainder as some Q is the remainder, T is the remainder, Q is the quotient. So N can be written as QR plus T. Okay, so this is by division algorithm, and this T has the property that it is strictly less than R and it is less than or equal to, greater than or equal to 0. Okay, so from this what will we get? So from this we will obtain that I have already shown this, that is A raised to T is element of this H. Now, is this possible? It is not possible if it is positive, because r is the smallest positive integer with that property. So therefore, that means this t should be 0. Now, when t is 0, I will get that n is equal to qr. Therefore, my c, which was a raised to n, is actually a raised to qr, but this can be written as a raised to r, the whole raised to q, which is actually b raised to q. So the c could be written as a power of b. So c is an arbitrary element, so every element could be written as a power of b. Therefore, that means this H is cyclic. So every subgroup of a cyclic subgroup is again cyclic. So that's an important result here. Okay, so this is the first section here. So all this thing, so this is the proof. I have also brought the proof here. Same thing has been taken here. So I'll share this with you. Okay, so it's the same idea here. You can just go through this, and this is the same thing here. Just you are using the division algorithm. Okay, now we'll introduce some other concepts also. So we are going to introduce an important result called Lagrange's theorem. So it's very important. So for that we need to set some basics here. Okay, suppose we are done with cyclic groups now. We are just generally going to groups here. So we are generally considering groups here. So suppose G is a group, and suppose H is a subgroup of G. For example, Z is a set of integers, and suppose my H is the set 3Z. So we can see that this is again a subgroup of Z, because identity 0 will be there. If you add two elements, it will be closed, because 3 plus 6 will be 9. So everything will be closed. Closure will be, you can check that, and also inverse of every element will be there. If you take A, the inverse will be minus A. So this 3 is a subgroup. Okay. Now we'll define what's a coset of. So when you have been given a subgroup, we can always define its coset. Okay. So cosets of H. Okay. So it is nothing but, suppose G is a subgroup, and G is a group, and H is a subgroup. The cosets of H are simply A into H. This will be called the left cosets, or H into A. This will be called the right cosets. So the theory is similar. So I'll just be considering only left cosets. Okay. So what do we mean by this A into H? Okay. A into H is nothing but so basically, one second. Okay. So yeah. So we have a group G. We have a subgroup H of that. So what do you mean by A into H? It's nothing but you take the elements of A, H, and you just multiply with A. Okay. So suppose my elements of H are this H1, H2, etc. Hn is there. So A into H is nothing but AH1, AH2, AHn, where the multiplication is the operation on G. Okay. So these are called the cosets of H. For example, let us illustrate this thing. Okay. So how do we illustrate? Suppose G is simply Z. Okay. Under addition, and my H is 3Z. Okay, again under addition, we know these are subgroups. So what is so here the operation is addition, so there is no meaning of A into H, so I'll just write this as A plus H here. Okay, so here the meaning is addition here, so I'll just be writing this as A plus H. So what is actually 0 plus H? Just think, what is 0 plus H? So you have to add every element of H with 0. So my H is actually, what is, first I'll write my H is actually 0 is there, 3 is there, 6 is there, 9 is there. Similarly, minus 3 is there, minus 6 is there, etc. It's an infinite group. So 0 plus H is again the same elements only. So it is minus 6, minus 0, 3 will be there, 6 will be there, 9 will be there. It will go indefinitely like this. So this is the one coset, 0 plus H. Now let us look at 1 plus H. That is another coset. What is 1 plus H? So what is it? Minus 6 plus 1 is minus 5 is there. Minus 3 plus 1 is minus 2 is there. 0 plus 1 is 1 is there. Again 3 plus 1 is 4 is there. 7 is there. 10 is there. So this is another coset. Okay, so this is how you define coset. Again, you can again define it again. What is 2 plus H? 2 plus H is minus 6 plus 2 is minus 4 will be there. Minus 1 will be there. 2 will be there. 5 will be there. 8 will be there. 11 will be there, etc., etc. So you can see that this is again a coset. Again, you can define, so it can be defined for every element. So what is 3 plus H again? So what is 3 plus H again? So 3 plus H is nothing but you take the elements of H and you add 3 to that. So it will be 3 plus minus 6 again. It is minus 3, 0, 6, 9. You are again in the same group, etc. Okay. So this is what you mean by coset. So what is a coset? So if you are given a group, so if you are given a group G, and if you are given a subgroup, the coset AH, Okay, so here it was addition, so that's why I wrote it as A plus H. So if it is generally if it's a group, so if AH is nothing but the set of all A into H. A into H means A is combined with this H, where H is element of capital H. So this will be called the cosets of H, capital H. Okay, in G, cosets of H in G. Okay, so these are actually the left cosets. There is also a concept called right cosets in which I will be adding it to the right side. So in that case, I will write this as simply H plus 0, H plus 1, H plus 2, the same theory over there. For abelian groups, both are just the same, but just try to understand it. So I will be only discussing about left cosets here. Right cosets also will have the similar, maybe similar theory development. Okay, so I hope you understand what is mean by coset here. So for that, first of all, to introduce a coset, you should also know uh, what is a subgroup. Only if you have a subgroup, you can define cosets accordingly. Okay, okay. So here, this is another example. If you're taking Z9, I would hope you understand what is Z9. Z9 is nothing but the set of 0, 1, 2, etc. up to 8 under addition modulo 9. So Z9 I am taking that, and of that I am taking a subgroup H036. So you can check whether this is a subgroup. You can check for closure, you can check for identity, and also inverse of each element will be there. Okay, and also we have also devised some other methods also. If it is finite, if it is closed, it will be a subgroup. So that is enough. So the 036 is a subgroup here. Okay, so in that case, where we have displayed some cosets here. We took 0 plus h is nothing but 036. Then again I took 1 plus h. I took it, got it as 1 plus 4 plus 7. Again 2 plus h. It was again 2 plus 5 plus 8. If you take 3 plus h, what will you get? If you take 3 plus h, it will be 3 will be there. Again 6 will be there. Again 9 will come, but it is addition model 9, so you will be getting it as 0. So that is it. Again 4 plus h also, you can again think what will happen. When you take 4 plus h, it will be nothing but 4 will be there, 7 will be there. Again 4 plus 6 is 10, and divided by 9 it is 4, 7, 1. So that's again the same element. Okay, so these are the examples of cosets. Now you have seen, you can see a pattern here. When you have already studied equivalence relations earlier, so we can see a pattern here that if you add all these cosets, what will you get? If you combine all these cosets, what will you get? You will be getting the entire set G. Earlier we took 3Z also, you can also observe that result here. So when you take all these cosets, you will get the entire group G. We will prove that formally, but just to make this observation now. And also we can see that the distinct cosets are entirely distinct. There are no common factors here. Okay, so if you take 3 plus h, actually you will be getting the original set back. So either two cosets will just be the same, or it will be entirely different. Okay, so we can see that 0 plus h and 1 plus h are entirely different, but 0 plus h and 3 plus h are just the same. So either cosets will be the same, or they will be entirely different. And when you take the union of all distinct cosets, you are getting the entire set G. That is, you have heard it right, cosets partition a group G. So cosets of a subgroup partition a group G. So cosets of a subgroup H partition a group G. So that's what we're going to prove here. So I hope you understand what do you mean by partition. We have already discussed about partition when we dealt with equivalence relation earlier. Okay, so what you're going to prove. So I hope you understand what is a partition. What is a partition? Do you remember that? So if you have a group G, partition is basically collection of a subgroups. If you have a group G, partition is basically a collection of subgroups of maybe subsets of G with the property that when you take the union of all those subsets, you will be getting the entire G will get, and also union of all this subsets, maybe AI will give you G, and also distinct sets will be different. AI intersection AJ will be disjoint. So distinct cells will be disjoint, and also there will be no common factors, and when you take the union you will be getting the entire set G. So that is what we mean by partition. Now we will prove that cosets will actually partition a cosets of a subset H will actually partition G. So that's the result we are going to prove it here. Okay, so very simple thing. If you understand the concept of partition, it's very simple. Okay, so first of all, this result is generally true for all subset. So in particular we are considering here only finite set now. Okay, so we are only considering finite groups here because we are going to bring an important result here. So generally for infinite groups also the cosets will partition the group. So here we are going to discuss only finite groups here. So after that, okay, so we'll prove some results here. First of all, suppose you have a set group G is there and you have a subset subgroup is there, H is there. Okay, we will be considering the left cosets here. Okay, so first we'll show that every element G belongs to some coset. Every element G belongs to some coset, and that coset is GH, right? Because so first of all you have to show that cosets will form a partition. That means you have to show that every element of G is lying in some coset. So if I take a G, I have to show that this G is lying in some coset. So definitely G will be lying in the coset generated by G itself. That is G is element of GH, because H contains the identity element. So when I take G into E, what will I get? I will again get as G. So G element of GH, because G can be written as some G into E. So G is there in G. So every element of G is there in some coset. So when you take the union of all these cosets, so you will get your entire set G. So union of GH will give you G. So that's the first result. Okay, in the step towards what you say, proving that cosets partition G. Okay. Now related to this, so if it's a, we have taken this as a finite set. Now we'll show that order of maybe some order of A into H. So where A is an element of G, or simply order of G into H. Order of G into H is same as order of H. Order of G into H is same as, so we'll see additional result apart from being a partition. So we'll show, so this is, since this is only finite elements, we can only talk like this, because infinite things orders will be infinite, so there is no use, there is no meaning to this thing. So we are taking here finite sets. So we are going to prove that order of GH is same as, order of a coset is same as order of the subgroup. I hope you understand what do you mean by order. Order is nothing but the number of elements in that set. So order is nothing but number of elements in this set. Okay, so we'll show that order of GH is therein is same as order of H. Okay, so how will you do that? It's very simple. We have seen these type of proofs before. So how is GH obtained? So first you write H. H contains H1 will be there, H2 will be there, etc. Hn will be there. Now GH is obtained by multiplying this H with G. So you will get this as GH1 will be there, GH2 will be there, GHn will be there. So anyway, it cannot go beyond these n elements. Okay, so that means order of GH is anyway less than or equal to order of H, because GH is obtained by precisely multiplying the elements of H with this G. Okay, so we will get GH1, GH2, Hn, and GHn will be there. So this is means order of GH is less than anyway it will be less than or equal to order of H. Okay, why I am telling it less than or equal? Because some elements when you multiply they can be the same. Okay, suppose two elements when I multiplied, so maybe GHI, and when I multiply GHJ, suppose I got the same result. Okay, so that's why I put this less than or equal to less than for a quotient. Okay, so suppose GHI is equal to GHG. So what is the meaning of this? So that means if some elements are same, that means the number of elements will actually be lesser than the number of elements of this H. So number of elements of will actually be less than the number of elements of this H. So suppose it is like that. So suppose some GHI is equal to some GHA. So when that happens, what is the meaning of this? Already G is a group, but by cancellation law, I will get this as HI is equal to HJ. So this situation cannot occur. That means that in this GH1, GH2, etc., GHN, all these elements should be different. No two elements can be the same, because if two elements are the same, that means you are getting HI is equal to HJ. So all these GH1s, GH2, etc., GHNs are actually different. So that means order of GH is same as order of H. Okay, so very important result from the case of finite cosets. So this is another important result. Order of a coset is same as order of a subgroup. Okay, again, finally to the partition thing. What is the partition? Partition means the sets are entirely disjoint or just the same. So I'll show that either, suppose I'm taking two elements here. Suppose I'm taking A into H, and and also I'm taking another coset which is BH. So I'll show that either AH is equal to BH, or I'll show that AH intersection BH is empty. So either the cosets are entirely the same or they are entirely disjoint. There is no scope for any intersection there. Okay, so how will you prove this? So this is the key to the partition idea. So when you have this, also we have shown that every element belongs to some partition. So every G was the element of some GH. So every element belongs to some partition, and also what you have got, these partitions are entirely disjoint. So this will get that. So these cells are entirely disjoint. That means this cosets will actually partition the set. So how will you prove this? Okay. So suppose we'll we'll take that AH intersection BH is non-empty. Suppose it is non-empty. We'll show that only this will happen. Only the possibility then is AH should be equal to BH. Okay, so we have the result that either the cosets are just the same or they are entirely different. So we'll assume that it is not entirely different. So we'll show that it's just the same. So we'll assume that AH intersection BH is not equal to phi, and we'll show that AH is equal to BH. So what do you mean by AH intersection BH is not equal to phi? That means there exists some element, maybe some H will be there with the property that it is there. So I'll take an element H is there with the property that AH intersection H element of H is so since there H is already there, so I'll call this some H1. Okay, so I'll call this as some H1. This H1 has a property that this H1 is lying already it is lying in AH, and also H1 is lying in BH. H1 is lying in AH, and also this H1 is lying in BH. Okay, so since H1 is lying in AH, I can write this as some maybe AH maybe I can write this as some AH2. Okay, so H1 is actually some AH2, and also since it is lying in BH, I can write this as some BH3. So I'll get this as AH2 is equal to BH3. Okay, since because H1 is lying both AH and also BH, so I can write this as AH2 is equal to BH3. Now we'll show that AH is equal to BH. So how will you show that? So these are basically sets. So first I'll show that one is a subset of other, and also other is a subset of this element. Okay, so first I will take that X element of AH. I'll show that this X is actually element of BH also. We'll prove that now. Okay, so how will you do that? Okay, since X element of AH, I can write X as some A into H, right? Since X element of AH, I can write X as some A into H. Now A I can write from this result as A is actually equal to BH3 H2 inverse, right? So A can be written as BH3 H2 inverse from this result. So I can write this X as BH3 H2 inverse into H. BH3 H2 inverse in H, where H3 H2 and H are there in H. So this means that, so these three elements are there and already in H. So since H is a subgroup, their combinations also will be there. So that means this will be element of B into H. Is that clear? So I took X as AH. I have shown that this actually lies in BH. So I took an X element of AH. I already show that this X is now lying in BH. How? Because A could be written as BH3 into H2 inverse using the result mentioned before. From that you will get that X element of BH. So similarly you can also think of the other thing. Same idea. Suppose I am taking Y element of maybe BH. So Y can be written as some B into H. Okay, some B into H. Okay. Okay. Now from this result, this B can be written as AH2 H3 inverse. So my Y will be written as now AH2 H3 inverse into H. That means this is an element of A into H, because H2, H3 and H are there in our subgroup H. Since this is subgroup, it is closed. Therefore, H2, H3 inverse H is actually element of H. That means Y is an element of AH. That means AH is now a subset of BH, and similarly BH also was a subset of AH. That means AH is equal to BH. So what have we got? Either AH intersection BH is equal to phi. If it is not phi, that means it is equal to, both are the same. So the cosets are either the same or they are entirely disjoint. Okay, so this was the result which we have proved here. So now we have got that. What we will summarize the discussion here. What we have got till now. Now we have got that if you take it considering finite groups. So we are taking finite groups. So G is a subgroup, finite subgroup, and G is a group. H is a finite subgroup. We have got that. First of all, order of the coset is same as order of the subgroup. One result. Again, next one was every element of G is there in some coset. Okay. Now next one we got that either the cosets are disjoint. Sorry, either the cosets are disjoint uh, or they are entirely either cosets are disjoint or they are entirely the same. So this means that the cosets actually partition the group G into cells of equal order. The cosets actually partition the group into cells of equal order, and in that partition also there will be one cell will be our H. Okay, why? Because if I take E into H, it will also be the simply the one coset H. So this cosets is actually partitioning the group G into cells of equal order, and of those one partition will be our H. Okay, now let us count the number of elements of G. Okay, now the elements of G will be, so the number of elements of G will be actually the number of elements of each partition. Okay, so I can so number of elements of G will be number of elements in the first cell plus the number of elements in second cell plus etc plus etc. But you know that all these cells have the equal order, all these cells have the equal number of elements. So if there are such cells, order of G can be written as R into order of H, because H is a part of that cell. So when you count the number of elements of G, what can I say? It can be partitioned into cells of equal magnitude. So okay, so because we have shown that different cosets have the same magnitude, so when you count the number of elements of G, I will be counting the number of elements in the first cell plus the number of elements in the second cell plus the number of elements in third cell, etc, etc. But all these number are same, so the number of elements in this cell is maybe I don't know, suppose it is maybe 10. Same, you will get 10 elements here also. Here also 10 elements will be, every element will have 10 elements. So when you take the full addition, when you collect the all the elements, what you will get? You will get number of cells R into 10. Okay, so using that same result, the order of element of G will be nothing but the number of elements R into number of elements in H, because H is also a coset. H is the coset EH, so it will also be a different cell here. Okay, so G can be written as R into order of H. What does this mean? This means that order of H is a factor of G. That is, order of H is actually divides order of G. So what you get here is that order of a subgroup divides order of a group. Order of a subgroup divides order of a group. So this is an important result here. This result is called the Lagrange's theorem. So order of a subgroup divides order of a group. So if I take a group element with 10 elements, I can definitely say that it will not have a subgroup with 3 elements. Why? Because the order of a subgroup should divide the order of the group. So what can I, why? So 3 cannot divide 10. So I can definitely say that this subgroup with 10 elements will not have a subgroup with, this group with 10 elements cannot have a subgroup with 3 elements. So order of a subgroup divides order of a group G. So this is the Lagrange's theorem, which was the part of this section. So it's very important. This is what the final part. So Lagrange's theorem states that, so they can ask you state and prove Lagrange's theorem. It states that order of a subgroup divides order of a group. Order of a subgroup divides a order of a group. So I hope you can write it down formally. So you have to write it down formally. How will you write it? First you show that you take the first you say you bring the setting here. You take a group G, then you take a subgroup H. Now you look at the cosets of H, AH. You show that this AH partitions G, and you also show that this order of AH is same as order of H. So with these two results, we will get that order of G can be written as R into order of H, where R is the number of partitions. Okay, so from that you will get that order of H divides order of G. Okay, so this is how we will prove Lagrange's theorem. We have illustrated each and every step here. Okay, and one more thing I'll do. One more corollary of this theorem is that every group of prime order is cyclic. Every group of prime order is cyclic. It's a very important result obtained from this result. Every group of prime order is cyclic. Okay, so it's very important, very easy to prove. Suppose if you take a group of prime order, okay, so if it is not cyclic, you will always get an element A will be there. So if you look at the subgroup generated by this A, suppose you are taking a group G and you are taking an element A there. Okay, so if you look at the subgroup generated by this A, what will you get? You should get it as G itself. Otherwise, what will happen? The subgroup generated by this A, its order should divide the order of G. Okay, but G is of prime order, so there is no, the only factors of a prime order are only factors of a prime number are either 1 or the prime itself. So if you take an element A which is not equal to identity in G, okay, the subgroup generated by that element will actually be G, because otherwise the order of this subgroup should divide the order of group G, but order of the group G is prime, so only factors of G are either 1 or P. That means order of A is equal to P, which is same as the order of G. That means G is actually being generated by this element A. Therefore, we can say that every group of prime order is cyclic. This is basically a simple result obtained from number theory using the Lagrange's theorem. Okay, so that's it here. Now we have finished this module. Okay, maybe I'll bring another class to you regarding some examples also. So that's it. So this is the end of the fifth module. Thank you.